So this is part 2. We're looking at the 6.4 equations here. Question number 3 says determine the general solutions to the following. Now, I'm also going to switch between degrees and radians as we're doing these, just so that you can see some in both. So let's do the first one here in radians. And also notice that these questions have some extra parts to them. So sometimes we need to transform our equations using identities before solving them. So looking at the first one here, I see I have a cos double angle. Remember that if you look at your identity sheet, there are 3 options for cos double angles. 3 options for cos double angles. I want one of the cos double angles that will maybe eliminate that plus 1. So is there a cos double angle that has a minus 1? Yes. It says 2 cos squared x minus 1, and then there's the plus 1 minus cos x equals 0. Now a little trick is that we want to try to get the same trig function. All right, now this is just an equation that we can solve, just like we were doing in our 4.4 equation. So we have a subtract 1 and add 1, so that will cancel each other out. So we're left with 2 cos squared x minus cos x equals 0. I see a squared. So whenever I see a squared, I'm going to think factor. Factor this. What can be factored out of these? Cos, right. So I'm going to factor out a cos, and I'm left with 2 cos minus 1 equals 0. Now, like any quadratic, once it's factored, we set each factor equal to 0. So we're going to have a cos x equals 0, and a 2 cos x minus 1 equals 0. We're almost done. Cos x equals 0, that one is done. But the other side here, I still need to get that cos part by itself. So if I add the 1, and then divide out the 2, we get that cos x equals 1/2. Are we done now? Okay, so we look on our circle, and we find these to be our answer. But for this question, we were actually asked to find the general solutions. So the general solutions mean that you could keep going around the circle an infinite number of times and find all the coterminal angles. So if you look at, here's pi over 2 and here's 3 pi over 2, the way that we could write that in a general form would be to say that if you start at pi over 2 and then you add or subtract pi n, or you could just say add pi n where n is, we'll just say add pi n where n is an integer. N stands for a number that you'd be, how many times you'd add or subtract pi. So basically, if I say pi over 2 plus pi n, that means I start at pi over 2, and if I add pi, I'd get to here. But then if I'd add pi again, I'd get to a coterminal angle. Add pi again, I'd get back to here. So you can basically keep adding pi n number of times and keep going around and around your circle. So that would be our general solution.
Wouldn't that be for one of them though?
So far we've found the general solutions just for the cos equaling 0. Now we need to find the general solution for pi over 3 and 5 pi over 3. So for pi over 3, we start at pi over 3, but I see that down here 5 pi over 3 is not nicely halfway across the circle. So for this one, we have to say the general solution is where we're going to add 2 pi n. So we get pi over 3 plus 2 pi n to keep going back to pi over 3. We would also have to do the same thing for 5 pi over 3. We'd have to add the 2 pi n to get the general solution. So again, you're starting at that spot and you're making your loop to go all the way back to that same spot. So again, those would be our general solutions, and there's 3 of them. Let's try the other example here. For example B, let's start by trading the 1 minus cos squared with sine squared from our identity sheet. And that's because 1 minus cos squared x does equal sine squared x. So now this helps us, because now my whole equation is in terms of sine. I also see that I have a sine squared. So that tells me I'm going to need to factor. But before we can factor, we should move everything to one side of the equal to sign. And it's nicest to have your squared as a positive. So I'm going to subtract my 3 sine x and add my 2 to the other side to equal 0. So I'm just moving my 3 sine x and my 2 over to the other side so that now it's in quadratic form. Where do we go from here? So these would be our factors. Now once we have it factored, we can set each factor equal to 0, which means we're going to get sine equals 2 and sine equals 1. Now there's a problem here. Sine equals 2. You guys, this is a unit circle. So this means that the opposite is 2 and the hypotenuse is 1. What do you know about that?
It's wrong.
It's wrong. It's not possible, right? You can't have an opposite that's larger than a hypotenuse. So this part of the question has no solution. Okay, you can't have sine be bigger than 1.
What's your 2 over 1?
So this means that our sine x equals 1 at pi over 2. But if I want the general solution, then we have to take our pi over 2 and add 2 pi n. Again, that represents that you're going to keep making loops back to that same spot as you go through the circle. So let's look at example C here. Let's start by changing our cotan into cos over sine. I'm going to do that because I see that cos and sine are both still in my question. So cos squared x will equal cos over sine times sine. Now what do you notice?
Those signs cancel.
The signs will cancel, exactly. So we're left with cos squared equals cos. Okay, this is good. I've got cos on both sides. And I see I have a squared. So as soon as you see a squared, you think, okay, I'm going to need to factor this. But before we factor, we'll move it all to one side. Yes, so we'll subtract the cos over to be with the cos squared so that everything is on one side of the equal side. Now how do we factor it? Then once it's factored, we just set each factor equal to 0. So cos x equals 0, or cos x minus 1 equals 0. And when I add that 1 over, we get cos x equals 1. So we have two answers here, cos x equals 0 and cos x equals 1. Now where does cos equal 0 and where does cos equal 1? So we'll get where cos is 0 is at 90 degrees or 270 degrees, and cos is 1 at 0 degrees and 360 degrees. So this one's a little bit different because this one, I see that I'm talking about all the 4 quadrant spots, right? We're talking about here, 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 and here. So is there a way that I could cover this using one general formula? Right, plus 90 in, right. Because if I want to go from here to here, I have to add 90. Here to here, add another 90, add 90, add 90, and I could keep adding 90s. And I would get to all those spots. Now, I made a mistake here, though.
Yeah.
Which one of these is not included?
180.
180, sorry. So we can't do it that way. Never mind. On recording, sorry. We have 90 and 270. So these would be adding 180s to get between the 90 and 270s. So one of our general equations would be x equals 90 degrees plus 180 n. Again, that's where you're adding 180 to get back to the bottom or up to the top. But then we have 0 degrees, and here we'd be adding 360 n, because we're going to be starting at 0 and have to go all the way around the circle to get back to 0, and then again. So here we're adding 360s at a time. Alright, so here we're changing the sine 2x into the 2 sine x cos x. Now I do have both cos and sine here, but there's nothing else that can simplify. So let's start by moving everything to one side of the equation. So we'll get 2 sine x cos x, subtract root 2 cos x equals 0. So I'm just moving it all to one side. And now I'm going to see if there's something that I can factor. Is there something common that I can factor? Cosine, right. I see that there's cosine in both of these pieces. So I can divide the cosine out. And then I'm left with 2 sine x minus root 2 equals 0. So now it's factored. Once it's factored, we set each factor equal to 0 and look it up on our circle. So you should come up with two answers, that cos x equals 0 and that sine x equals root 2 over 2. Now, if we look on our circle, cos x equals 0 at 90 degrees and at 270 degrees. And sine equals root 2 over 2 over here at 45 degrees and over here at 135 degrees. So 45 degrees and 135 degrees. Now, again, we can make the general solutions of those. So question E, let's do this one in radians again. And I see that cosecant is something that's kind of a little different in this question, but we could change that to sine. So we get 2 sine x equals 7 minus 3 times 1 over sine x. If I change cosecant to 1 over sine. Now, we don't like fractions in these questions, right? The fractions make it difficult. But how can I get rid of a fraction? You multiply, right? We can multiply every piece of this by a sine x, just like we did with our rational function unit. So if we multiply every piece by sine x, then the sine x in the denominator and the sine x we're multiplying by will eliminate each other, so we won't have any fractions left. So here we're going to get 2 sine squared x equals 7 sine x subtract 3. So from here, let's move it all to one side so that we can factor. So we're going to subtract the 7 sine x and add the 3 all to the other side of the equation. Now this we'll have to factor using decomp. So our factor should be 2 sine x minus 1 and sine x minus 3, which means I have sine is 1/2 or sine is 3. But remember, sine can't equal 3 because that means the opposite is bigger than the hypotenuse, so we can't have that. But we can look at our circle and find where sine is 1/2. And sine is 1/2 here in radians, where x is pi over 6 and 5 pi over 6. So those would be our particular solutions. We can make the particular solutions into general solutions by adding the 2 pi n. Okay, so again, the particular solutions are just listing your solutions, but then the general solutions are when you add on the 2 pi n to speak for all solutions as you keep going around and around. We will then try the following textbook questions. This is now page 320, so part of section 6.4.